The tremendous blast is a thought that has framed how we decipher the universe, outlining the foundation of current cosmology. According to Einstein's speculation, also known as coarse-reading cosmology, the enormous explosion marks the moment the universe began its development, indicating the production of all matter, energy, and existence. This event happened roughly 13.8 billion years ago and led to the colossal universe we observe today. However, recent developments in cosmology suggest that the colossal blast probably wasn't the absolute beginning. Instead, it may have been a stage before the gigantic explosion, of comparable significance in shaping the universe as we understand it. This pre-period is known as unstoppable growth. Development is quite possibly one of the most interesting aspects of present-day cosmology. It suggests that before the hot, dense phase of the enormous blast, the universe went through an unbelievably fast and dramatic expansion. During this period, the universe was duplicating in size at a staggering rate. To precisely represent how extreme this expansion was, assuming a smaller universe's beginning, it would have expanded from smaller than an atom to incomprehensibly larger than the entire observable universe within a minuscule fraction of a second. This expansion took approximately a quadrillionth of a second. Although this stage didn't last long, it played a crucial role in shaping the universe. When the inflationary stage ended, the energy driving this expansion was released into space, heating it up and creating the matter particles that make up everything we discover in the universe. In many ways, this development is the precursor to what we consider the immense blast. While the theory of expansion is widely accepted in cosmology, many unanswered questions remain. For instance, we still don't understand what triggered the expansion, what caused it to stop, or how long it lasted. These are open inquiries in cosmology, and answering them is crucial for a deeper understanding of the origins of the universe. Before expansion, the universe was in an incredibly dense, small state, often referred to as a singularity. From this singularity, development began and eventually led to the formation of atoms, particles, stars, and galaxies. Initially, the concept of the massive explosion seems straightforward, but contemporary cosmology proposes a more complex picture. Some theories suggest that the universe underwent a phase before the gigantic blast. During this stage, expansion caused the universe to accelerate at an extraordinary rate, by a factor of 1 trillion in just a fraction of a second. This rapid expansion was driven by an unusual form of energy that permeated empty space. When expansion ended, the energy that had powered this development transformed into atoms, heating the universe and leading to the hot, dense state known as the gigantic blast. This inflationary stage was cold and empty, but it set the foundation for the production of matter and the universe we see today. One of the more theoretical ideas in modern cosmology is the concept of eternal expansion. This theory proposes that expansion didn't stop at the same time everywhere. Rather, it ended intermittently, creating different pockets, each of which could be its own universe. If this is correct, our universe would be just one of many. According to eternal expansion, there could be an infinite number of universes, each with its own set of physical laws and constants. This is where the concept of the multiverse comes into play. The idea that our universe may be one of many, or even an infinite number of universes. If this theory proves true, it could explain why the universe is so finely tuned for life. In this multiverse scenario, every possible combination of physical laws could exist in different universes, and we just happen to live in one where conditions are perfect for stars to form and provide the elements necessary for life. While ideas like eternal expansion and the multiverse remain speculative, the concept of expansion itself is supported by observational evidence. The strongest support for expansion comes from the cosmic microwave background radiation, CMB, the oldest light in the universe. The CMB was released approximately 380,000 years after the colossal blast when the universe had cooled enough for atoms to form. At that point, the universe became transparent, and this light has been traveling across the cosmos ever since. By studying the CMB, cosmologists can essentially take a baby picture of the universe. This light provides clues about the universe's earliest moments, helping scientists understand what happened soon after the immense blast and offering support for the inflationary model. One of the most significant discoveries came from the European Space Agency's Planck satellite, which took detailed images of the CMB. These images revealed subtle variations in temperature in the early universe, and these variations matched the predictions of inflationary theory. This evidence strengthens the idea that expansion isn't just a speculative theory but a fundamental part of our understanding of the universe's origins. Understanding the tremendous blast and what came before it requires unifying two of the main theories in modern physics: Einstein's theory of general relativity and quantum theory. General relativity describes the large-scale structure of the universe, including the behavior of galaxies, stars, and planets, while quantum theory explains the behavior of particles on the smallest scales. To answer the fundamental questions of cosmology, such as what the universe is made of and where it came from, scientists must develop a theory that unifies these two frameworks. This would not only help us understand the colossal blast but also the conditions that led to it. One of the most astonishing aspects of the universe is its vast scale. The farthest objects we can observe are about 47 billion light-years away, meaning the observable universe has a diameter of approximately 94 billion light-years. This might seem paradoxical, given that the universe is only 13.8 billion years old. How can the observable universe be larger than the distance light could have traveled in that time? The answer lies in the fact that the universe has been expanding since its inception. As the universe expands, the distances between objects increase, making some distant regions appear farther than they would if space were static. Most researchers believe that the universe extends far beyond the observable portion. In fact, it's possible that the entire universe is infinite in size. The observable universe is simply the part we can see, limited by how much time light has had to reach us. However, beyond this boundary, the universe may continue indefinitely, holding mysteries yet to be uncovered. Has needed to travel since the tremendous blast, there might be huge areas of the universe that we will always be unable to see. While it's conceivable the universe is boundless, the inquiry remains: is there anything beyond the universe? Most scientists perceive this with a little uncertainty. If the universe is endless, there is no outside to it. The universe would basically continue perpetually. Regardless of whether the universe is finite, it probably wouldn't make sense to talk about anything beyond it. Beyond would refer to something outside of space, which is one of the fundamental properties of the universe. So, the possibility of something beyond the universe might not have any physical meaning. Just as the beginning of the universe is a subject of great study, so too is its inevitable end. The best current estimate is that the universe will keep expanding perpetually. This is due to a strange phenomenon known as dark energy, which is responsible for the universe's accelerated expansion. Before the discovery of dark energy, researchers believed that the universe's expansion would eventually slow down due to the gravitational pull of matter. There was even a possibility that the universe could stop expanding and start contracting, leading to a big crunch. However, dark energy appears to be pushing the universe apart at an increasing rate. If the universe continues expanding at this speed, it will continue to grow endlessly, ultimately reaching a state where galaxies are so far apart that they become isolated. In this scenario, stars would burn out, planets would drift away, and matter would eventually decay. This is known as the Big Freeze or heat death of the universe. The story of the universe, from the Big Bang to its possible end, is one of the most crucial and complex narratives in science. Despite our significant discoveries about the origins of the universe through the theory of cosmic inflation and the study of the cosmic microwave background radiation, many questions remain unanswered. What caused inflation to start and stop? What lies beyond the observable universe? Does a multiverse exist? If so, how many other universes are there? As scientists continue to explore the universe using advanced technology and theories that connect quantum mechanics with general relativity, we will undoubtedly gain deeper insights into these mysteries. The journey to understand the universe is ongoing, and every discovery brings us one step closer to answering the fundamental questions about our existence. The study of the universe's origins and structure is not just a scientific endeavor. It also raises philosophical questions about existence, reality, and our place in the cosmos. One of the most important topics in cosmology is the nature of dark matter, which is believed to make up about 27% of the universe's total mass energy content. Unlike normal matter, dark matter does not emit, absorb, or reflect light, making it invisible. It can only be detected through its gravitational effects on visible matter. Understanding dark matter is crucial for explaining the formation and behavior of galaxies. Ongoing studies and observations have provided insights into its properties, but its exact nature remains elusive. Several candidates for dark matter particles have been proposed, including weakly interacting massive particles, WIMPs, XIONs, other exotic particles. However, no direct evidence for dark matter particles has been found so far. The search continues through laboratory experiments, cosmic observations, and computer simulations that model how dark matter influences the large-scale structure of the universe. Another key area of research is dark energy, the mysterious force driving the universe's accelerated expansion. Dark energy makes up about 68% of the universe's total mass energy content. Its discovery was unexpected and led to various hypotheses, including the cosmological constant proposed by Einstein, dynamic fields like quintessence, which suggest dark energy may evolve over time. Understanding dark energy is crucial because it determines the ultimate fate of the universe. Scientists are studying its effects on cosmic structures and trying to determine whether it remains constant over time or changes. In addition to dark matter and dark energy, the study of large-scale cosmic structures offers valuable insights into the history of the universe. Observations of the cosmic web, a vast network of galaxies, clusters, and filaments, have revealed how matter clumps together under gravity, forming the complex structures we see today. Supercomputer simulations help scientists understand how these structures formed over billions of years and continue to evolve. Astrobiology also intersects with cosmology as researchers investigate the conditions necessary for life beyond Earth. The search for exoplanets, planets orbiting stars outside our solar system, has intensified, with thousands discovered in recent years. Some of these exoplanets are located in their stars' habitable zones, where conditions might be suitable for liquid water to exist. By studying these distant worlds, scientists hope to learn more about the potential for life elsewhere in the universe. Finally, the role of fundamental physics in cosmology cannot be overstated. The quest for a unified theory that merges general relativity with quantum mechanics continues to challenge physicists. Theories such as string theory, loop quantum gravity, aim to bridge these two areas and explain phenomena like black holes and the origins of the universe. As technology advances, so does our ability to observe and interpret cosmic phenomena. Space telescopes like the James Webb Space Telescope, JWST, are revolutionizing our understanding of the universe by providing unprecedented details about distant galaxies and cosmic events. With every groundbreaking discovery, we move closer to unraveling the mysteries of the universe's formation, evolution, and ultimate fate. The study of the cosmos is a vast and intricate tapestry of scientific inquiry and philosophical reflection. From the fundamental forces that shape massive structures to the search for extraterrestrial life, our exploration of the universe is a testament to humanity's enduring curiosity. As we strive to answer these profound questions, we gain a deeper appreciation for the immensity and complexity of the universe.